Dear friends, after getting an idea of how to select a pump and deciding upon the motor capacity, the final component in the design of solar photovoltaic pumping system is arriving at the size of the solar module. So the objective of this lecture is to just do a quick revision of some concepts of solar PV module, that is what exactly is a solar module, and then with the help of one or two case studies, we will try to internalize the concept of the design of solar PV panels. Okay. So let me just in a brief fashion explain you what exactly is the system we are talking about. So we are talking about sizing of or design of a PV array, photovoltaic array, which would generate the direct current which would go into a solar inverter, convert itself to an alternating current and help us drive a pump. If it is not an AC pump as is seen in the case, then we need not use a solar inverter. Instead, we would use simply a solar converter or a solar controller unit. Okay. In our calculations, we can assume a certain value of efficiency for solar inverter and then arrive at the photovoltaic array sizing. Okay. Now, before going into the sizing concepts, let me try to explain you what exactly is the solar module. This solar modules in the market you would have seen in the form of solar array. Solar array means it is made up of number of solar modules, and solar module means it is made up of number of solar cells. So one solar cell typically would deliver a very smaller output. Now, for example, this solar cell which is shown over here, it delivers an output of about 0.25 watt peak. Okay, so when there is a peak solar radiation available, then the maximum power which is delivered by a single solar cell is about 0.25 watts. Okay, so a typical solar cell size would be like 125 mm by 125 mm. Okay, and this number of solar cells, they are connected in series. Okay, so when you are connecting it in series, the output of the solar cell would increase, right? And it is connected in a way so as to deliver a minimum output of, let us say, 3 watt bar up to maximum output which is expected from a solar module is 300 watt bar. So solar module is comprises of number of solar cells which are connected in series, and the maximum output of this module is 300 watt bar. One can have a solar module of a smaller capacity like 3 watt bar peak. Okay, so 3 watt peak is the smallest capacity one can expect from a solar module, but the modules which are generally available in the market for solar pumping, they come with the capacity of about 300 watt peak. Okay. Now, as we have seen that even for pumping application, if you want to pump even we use a 1 horsepower pump, which is about 746 watt, one gets a clear idea that a single module is not enough. So we need to then look for number of modules which are connected in series and parallel, and these modules, when they are connected in series and parallel, they would give us what is known as the solar PV array. Okay, so solar PV array comprises of number of modules, the maximum capacity of which is 300 watt bar, and then depending upon how they are connected, we would get the desired current and the desired voltage. Okay, so in order to select the module, and in order to select a PV array, uh, what you would require is you would require an information on the motor. Okay, so we had already selected a motor capacity, and in the last lecture we discussed as to how from the requirement of the water, from the total dynamic head, we arrive at the capacity of the pump and capacity of the motor. So motor input calculations can be done for a given location where we know the head and where we know the flow rate and we know the efficiency of the motor and pump. Okay, so this we had already discussed. So in order to arrive at the module selection and in order to arrive at the PV array selection, we need to know the motor input. Then we know that an inverter is in between the PV array and the solar pump. Okay, so if it is a AC pump, and in that case we need to know the inverter efficiency. If there is a DC pump, then we need not know the inverter efficiency, but in that case the controller efficiency has to be noted down. The selection of a solar PV module or a solar PV array is a function of the location, and by location we mean the availability of solar energy. So solar energy data, or it is known as solar insolation data, it is available, and that solar energy data has to be converted in terms of energy available uh, in a day. Okay, so for example, we know that the maximum solar insolation available is 1000 watt per meter square. So 1000 watt per meter square is the peak availability, and from morning to evening this availability is going to change. So typically we might have in a tropical climates, for example, solar sunlight for 8 to 10 hours. So in such a scenario we need to convert it into, and that 8 to 10 hours we won't be getting a peak solar sunlight. Okay, but we can convert that availability of solar energy into an equivalent of 1000 watt per meter square availability in terms of solar hours. Okay, so sunshine hours, for example, if you have actually 8 hours of solar energy, and that 8 hours every hour you are not getting 1000 watt, but it can be converted into an averaged out into, let us say, a sunshine hours of 5, uh, delivering an average of 1000 watt per meter square. Okay, so this way, so solar insolation data available would help us do the selection of the module. And then we need to know the output per module. So I talked about the output per module, that maximum output per module is rated output per module maximum is 300 watt peak. Okay, 300 watt peak, and that has to do with the way we are connecting the solar cells. From this, we can calculate the number of modules and we can arrive at the size of the array. Voltage and current, okay, is a function of how you are connecting the cells, whether you are connecting the cells in series or whether you are connecting the cells in parallel. If the cells are connected in series, okay, if the cells are connected in series, let us say that you are having each cell of 2.5 watt and you are connecting 4 cells in series, 2.5 watt, and it is of certain voltage. Okay, so then the output is going to increase, no doubt about it. Even if you are connecting series or parallel, the output is going to increase, but the current would remain the same and voltage will increase. Okay, so this has to be kept in mind. So if you want to increase the voltage, if you want to increase the voltage of the module, then we need to connect the cells in series, because each cell is going to deliver a small voltage and our requirement of voltage is high. So depending upon our requirement of voltage, we need to connect the number of cells in series. Okay, and how is that calculation done? How much is to be connected in series and all that? That would depend upon just a algebraic multiplication. So number of cells in series into the voltage per cell would give you the voltage per module in that, for a given module. Okay, and if you want to increase the current and keep the voltage the same, then we need to connect the cells in parallel. Okay, so these two things you need to keep in mind. These are the very important thumb rules which we should keep in mind, that if you want to increase the current, then we need to uh, put the cells in parallel. If you are if you want to increase the voltage, then you need to put the cells in series. Okay, so putting the cells in series would increase the voltage, putting the cells in parallel would increase the current. Okay, with this understanding, we will now try to solve a numerical which would help us understand the concept much better. Okay. So let us move to the numerical as to how do we actually select a PV module. Okay. So let us take a typical case. For example, first I will take a case of a DC pump. Okay, you want to size, or you want to select a PV array or a PV module. Okay, size for a DC pump. Now, when you say that it is a DC pump, there is no inverter. Okay, right? And let us say that this pump is of a capacity 1 HP, 1 horsepower. So 1 horsepower, is typically 746 watts. 746 watt. Okay. And let us say that the motor efficiency is 85%. Okay. And each module, each module what is a module? Module is a combination of number of cells. Let us say that there is a one module, and this module has 36. How many cells are there? 36 multicrystalline silicon cells. Okay. Silicon cells. So there are each module now is given that it has got 36 multicrystalline silicon cells. The cells could be multicrystalline, the cells could be monocrystalline. Okay, I'm not going into the cell technology right now, and it is arranged in a matrix of 9 by 4. Okay, 9 by 4 matrix, and it's also given that the cell size is 125 mm by 125 mm. Okay, and the efficiency of the cell is 12%. 12%. Okay, so now let us do the calculations. So the motor input in terms of this is 0.746 kilowatt, that is 1 horsepower, upon 0.85, because the efficiency is given, and that is around 0.87 kilowatts. Okay. Or if you want it in watts, it is around 870 watts. So this is what is to be supplied to the motor. Okay, and I am assuming that the controller efficiency is 100%. Controller efficiency is 100%. There is no inverter because it is a DC pump. Okay, DC pump. Now, if you want to calculate the number of modules, then we need to calculate how much is the output per module. Okay, so output per module is not given, so you need to calculate output per module. So it would be what? It would be cell area into the cell efficiency into the 1000 watt per meter square, which is the ideal peak solar insolation. It's a peak solar insolation. Okay. So this into this efficiency is the output of the solar cell. Okay. Into the cell area would give you per module. So this way, if you do the calculation for the total cell area, then the output per module is around 67.5 watts. Okay, 67.5 watts, and then you get the number of cells is 870 watt upon 67.5. This is all watt peak. Okay, watt peak, and this is around approximately 30. Okay, 30. So this way we have calculated the number of modules required. Okay, number of modules required. Okay, so this way, this is one application, one problem wherein we have selected a PV module for a DC pump of capacity 1 horsepower. Okay, knowing the efficiency of the pump motor, and by knowing what is the output of the what is the area of each module and what is the efficiency of the module. So you are given this data. Okay, this data is available. And how do you get this data? This data is available from the manufacturer's catalog. Manufacturer's catalog. Okay, catalog. All right. So this way you need to be clear on the calculations. The second problem I would like to do is the problem which we had discussed in the last lecture about a pump. Okay, and this pump we had considered for a vertical lift of 42 meters. Okay, if you have forgotten this, kindly revise the video which we had done on the pump selection. So 42 meters, and then there is a frictional loss of, we talked about 2.1 meters, which means this is total dynamic head of 44.1 meters. This is a total dynamic head. Okay, and in this case we consider that it is a AC pump. AC pump, again, ideally we would consider that it has got an inverter which has got a significantly high efficiency, of around 85%. Okay, and then there are some system losses which again gives you an efficiency of 80%. Okay, 80%. So you need to now, if you remember our calculations, I'll just revise the calculations in brief. We had calculated the hydraulic power as rho GQH, and we had taken the rho as 1000 kg per meter cube is the density. We had taken the acceleration due to gravity as 9.8 meter per second square. We had selected this 7 meter cube as the requirement of water, and this was giving you 44.1 as a total head. Okay. So this is your Q. It is not Q dot, it is Q. So that gives you around let us say 840. This is 30 in terms of watt hour. I will calculate it as 840. You have divided by 3600. You will get divided by 5 hours. We have taken it as 5 hours, and you will get the rating of 168 watts. Okay. Why this 5 hours? We have talked about This 5 hours is the average sunshine hours, and we talked about how this average sunshine hours are arrived at. We said that actually the sun would maybe it's available from 8 a.m. to, let us say, 4 p.m. or 6 p.m. But the solar energy would not be 1000 watt per meter square. So on the average, this would be equivalent to, this would be less than 1000 watt per meter square per hour. Okay, so this has to be converted to equivalent of 1000 watt per hour, and that comes as 5 hours. Okay, so that is why we are taken it as 5 hours. So this is average sunshine hours, and this we need to get it from the climate data. And there is also a NASA website on which this average sunshine hours can be obtained. Okay, or you can actually measure the sunshine at your place. Okay. So from this data, we can now go for sizing. So 168 hours, and we had to consider the motor efficiency as motor pump efficiency as 30%. So we had got the input as the motor input as 168 upon 0.3. If you remember these calculations, and that was around 560 watts. Okay. So now how much module size we need to do, right? So for that we need to, for sizing the solar PV panel, okay, we need to first include the inefficiencies. So 560, and we need to include this efficiency and this efficiency. So that upon 0.85 gives us 660 watt, and then this 660 watt upon 0.8 would give us 823 watt. Okay, and let us say that each module has an output of 300 watt peak. So you would require 823 by 300 watt peak. So this is around 3 modules is what you would be requiring for your pumping application. Okay, so this is how we arrive at the PV panel sizing for pumping application. Okay, thank you very much. Bye for now.